Welcome back to the Deep Dive with us. Today we are diving into the crisis in cosmology. And this isn't, your typical science debate. We're not talking about a small argument over a footnote in a paper.
No, not at all.
When we talk about a crisis in cosmology, we're talking about a conflict so deep, so profound, that it really threatens to rewrite our fundamental understanding of the universe.
That's absolutely right. The stakes are that high. It's a confrontation right at the heart of what we thought was our most successful scientific theory.
So our mission today is to dig into the research. We've got a stack of it here. Everything from the JONG satellite data to these incredible measurements from the Hubble Space Telescope.
And we're going to try to unpack this massive, persistent disagreement over just one number, a single critical number that defines how fast the universe is expanding right now.
A number cosmologists call H0.
H0, exactly.
And you, our listener, you should really care about H0 because this number, it's like the Rosetta Stone for the entire cosmos.
It really is.
It holds the key to everything. How old is the universe? How fast is it growing? And, what's its ultimate fate going to be billions of years from now?
If we can't agree on this one number, we can't really agree on the universe's life story. It's that fundamental.
And the conflict is so big it's even got its own name, right?
It does. They call it the Hubble crisis.
Yeah.
On one side, you have this beautiful, elegant theory of the cosmos, what we call the standard blueprint.
And on the
other side, you have our most precise, careful, recent measurements of the universe around us. And they just do not match. It's an incompatibility that's only gotten worse as the data has gotten better.
Okay, so let's set the stage for this whole deep dive with an analogy. I think this will really help.
Great idea.
Imagine the entire universe is. Let's say it's a car on a cosmic highway. And it's constantly expanding, constantly accelerating.
Okay, I'm with you.
That number, H0, is the current reading on the speedometer.
Yeah.
Just want to know, how fast is the universe going right now?
And to do that, we've basically built two phenomenal speedometers. And they work in completely different ways.
Two speedometers.
The first one is the early time speedometer. Now, this one doesn't look at the road right now.
What does it look at?
It looks back at the car's original design specs. At the roadmap that was written when the universe was just a baby, only 380,000 years old. It uses that ancient map, applies all the known laws of physics, and it predicts the speed the car must be going today.
It's a calculation, a prediction based on the past.
Exactly.
And the second one, the late time speedometer.
That one is mounted right on the dashboard of the car, right here in our local neighborhood. It uses direct, modern observations of things. Think of them as cosmic mile markers on the highway to measure the speed right now.
So it's an empirical reading, not a prediction.
Precisely. And the shocking part of this whole crisis is that both of these speedometers are considered perfect. They've been checked, double-checked, triple-checked.
And they're giving us two different speeds.
Two different speeds. And the difference between them is so large that it's statistically almost impossible for it to be a random error if our current understanding of physics is complete.
Which means one of two things. Either one of our speedometers is broken in a way we just can't see.
Which seems very unlikely given the precision we're talking about.
Or, and this is the exciting part, the rules of the road themselves, that cosmic blueprint, the standard model of cosmology, it's incomplete.
And that's the hunt for new physics.
Okay, let's unpack that blueprint. Let's start with the nice and tidy picture we thought we had before this whole crisis blew up.
Right. So the standard blueprint has a name, the Lambda-CDM model.
Lambda-CDM.
It stands for lambda cold dark matter. And for the last, 2 decades or so, it's been the foundational theory of modern cosmology.
And it's the standard model for a reason, right? It's been incredibly successful.
Incredibly. It describes the universe across this massive range of observations. I mean, from the shape of galaxy clusters today, all the way back to the oldest light in existence.
Yeah.
It just works with remarkable accuracy.
It's the closest thing we have to a rule book for the entire universe.
It is. So let's quickly define the parts. The CDM is cold dark matter. This is the invisible, slow-moving stuff that makes up about 5 times more of the universe than regular matter.
The stuff we can't see.
Right. It doesn't interact with light, but it provides the gravitational scaffolding that holds galaxies together. Without it, they just fly apart.
And the lambda.
Lambda is the cosmological constant. It represents dark energy. This is that mysterious, repulsive force we discovered back in the late 90s that's actually making the expansion of the universe speed up.
So it's the engine that's pushing the gas pedal down.
That's a great way to put it. And the reason Lambda-CDM became the standard is because of its predictive power. It accurately predicted things like the pattern of peaks and troughs we see in the ancient light from the Big Bang.
The cosmic microwave background?
The CMB, yes.
Yeah.
And it also predicted these things called baryon acoustic oscillations, or BAO. For decades, this model has just been rock solid.
And right at the center of this blueprint, the thing that connects the past to the present is the Hubble constant, h0.
Exactly. h0 is the value that defines the universe's current expansion rate. The technical definition you'll hear is that it's the number that converts distance into recessional velocity.
Okay, let's break that down. If you look at a faraway galaxy, how fast is it moving away from us just because space itself is stretching?
h0 tells you exactly that. For every unit of distance you look out, let's say a megaparsec, which is about 3.26 million light years, h0 tells you how many kilometers per second faster things are moving away from us.
So a high h0 means a fast, maybe younger universe. A low h0 means a slower, older universe.
You've got it. It's the ultimate reality check for our entire cosmic model. It links the physics of the universe's infancy to what's happening today. If the physics in between is correct, the number from the early universe must match the number we measure today.
And that brings us to the tension, the fight in the data. They don't match.
They don't. And the disagreement is stark. The predictions from the early universe, seen through that Lambda-CDM lens, they all point to a slower expansion rate.
And the direct measurements.
The observations in our local present-day neighborhood, the late-time probes, they insist on a significantly higher rate.
And we're not talking about a tiny rounding error here, are we?
Not at all. The discrepancy, the tension, has been consistently measured at somewhere between 4 sigma and 6 sigma.
Okay, sigma. Let's explain that. That's a measure of statistical certainty, right?
It is. In particle physics, for a result to be called a discovery, you need a 5 sigma confidence. That's a 1 in 3.5 million chance of being wrong, just due to random luck.
So when something hits 4 or 5 sigma, you stop calling it an anomaly. You start taking it very, very seriously.
Exactly. The Nobel laureate Adam Rees, who leads one of the teams, pointed out that with the amount of data they have, there's only a 1 in a million chance that they're wrong just because of an unlucky draw. We are way past the point of shrugging this off. We have to operate under the assumption that this tension is real.
And if it's real, it means that standard blueprint is missing something.
Something big. It means the model that's worked so well for so long is either incomplete, or maybe it's just an approximation of a reality that's far more complex.
So how did we get these two warring numbers? Roughly 67.5 on one side and 73 on the other. Let's dig into the two measurement camps.
Let's do it. The first camp, the one that gets the slower expansion rate, gets its number by looking at the early universe. And their main tool is the cosmic microwave background, the CMB.
The baby photo of the universe.
That's the one. The echo of the Big Bang. The ancient light that started traveling when the universe was only 380,000 years old.
And missions like the Planck satellite have mapped this light in incredible detail.
Incredible detail. Planck and ground-based telescopes like the Atacama Cosmology Telescope, or ACT, they've mapped these tiny, tiny temperature differences in this relic radiation.
So let's go back to our car analogy. This method is it's like looking at the original blueprints for the car and calculating how fast it should be going now, based on its engine specs from the very beginning.
A perfect analogy. You look at the initial conditions, you apply the standard rules of physics, and you project forward 13.8 billion years to predict the speed today.
And how do they do that from a bunch of hot and cold spots?
Well, those temperature spots in the CMB, they reveal these things called acoustic peaks. They're like harmonic notes frozen in time. The size and the spacing of those notes depend directly on things like the density of matter and the expansion rate of the universe at that time.
So you plug those ancient numbers into the standard model.
And it spits out a prediction for today.
And what speed does the blueprint predict?
Well, Planck data gives us a very precise number, 67.5 plus or minus 0.5 kilometers per second per megaparsec. The error bars are tiny. It's one of the most precise measurements in all of science.
And what makes this camp so confident is that it's not just one measurement, is it? Everything from that era agrees.
That's the key. It's internally consistent. The recent independent data from the ACT telescope confirms the Planck results. And another method, using baryon acoustic oscillations, or BAO, also lands on that lower number.
Okay, we have to pause on BAO. What exactly are those?
So BAO are essentially fossils of sound waves that traveled through the hot, dense plasma of the early universe.
Sound waves in space.
Before the CMB formed, the universe was like a hot soup of particles and radiation. And pressure waves, just like sound waves in air, rippled through it.
And when the universe cooled down, those ripples just froze.
They froze in place, yeah. They left a measurable, distinct pattern in how matter is distributed across the universe today. We can see it in galaxy surveys.
And this pattern acts like a ruler.
A standard ruler, exactly. We know how big that ruler was in the early universe, so by measuring how big it appears to us today across billions of light years, we can calculate how much space has expanded. And that method, which is tied to the same early physics, strongly reinforces the lower prediction of 67.5.
So the early universe camp is really solid. All their evidence points in the same direction.
It does. Which brings us to the other camp, the late-time local measurement team. And they say, forget the predictions from the baby photo. We're going to measure the speed right now directly.
And this is mainly the work of the SH0ES collaboration, that's supernova, H0, for the equation of state of dark energy.
Led by Adam Rees using the Hubble Space Telescope.
And their method is called the cosmic distance ladder.
That's right. It's this amazing feat of cosmic surveying where you use a series of interlocking milepost markers to measure distances farther and farther out.
I like the ladder analogy. Each rung helps you get higher, but if that first rung is wobbly, the whole thing could be off.
A very real concern. The method relies on finding a couple of types of celestial objects that have a known, reliable brightness.
Tell us about that first rung.
The first, closest rung uses stars called Cepheid variables. These are bright stars that pulsate. They get brighter and dimmer at a very regular rate. And here's the magic. That pulsation period is directly linked to their true intrinsic brightness.
So they're like standard light bulbs. If you know how fast one is blinking, you know exactly how bright it's supposed to be.
You've got it. So you measure how bright it appears to us, compare that to how bright you know it really is, and you can calculate its distance with amazing accuracy.
And that lets them calibrate the distances to nearby galaxies.
And that calibration allows them to climb to the next, much higher rung on the ladder.
Which would be?
Type Ia supernovae.
Exploding stars.
Yes, and these are crucial. A type Ia supernova is what happens when a white dwarf star in a binary system steals too much matter from its companion. It hits a critical mass and boom, a massive thermonuclear explosion.
And the key is that they all explode in basically the same way.
With an almost identical peak brightness. They are the ultimate standard candles. Because they're so bright, we can see them billions of light years away. They're our most distant milepost markers.
So the SH0ES team spent, 30 years using Hubble to link the nearby Cepheid measurements to these more distant supernovae.
A 30-year marathon. They calibrated over 40 of these markers. Adam Rees called it Hubble's magnum opus because of the painstaking precision involved.
And the result, after all that work, what does the cosmic dashboard speedometer say?
Their number has consistently been much higher. 73 plus or minus 1 kilometers per second per megaparsec.
So 67.5 from the ancient past, 73 from the here and now. That gap, it might sound small, but cosmically, it's a chasm.
It is. And just like the early time team, the late time camp has internal consistency. Other local measurement methods, like the Mega Maser Cosmology project, which uses a completely different geometric technique, also land right around that higher value.
So both camps are internally robust, which makes the contradiction itself the most robust finding in cosmology.
It really is.
Okay, so this is where we have to be good scientists. Before we jump to new physics, we have to scrutinize the measurements. We have to be absolutely sure this isn't just a very, very sophisticated mistake.
Absolutely. The community has spent the last decade trying to find the flaw, trying to poke holes in one of the measurements, especially that local distance ladder.
Because it has all those steps, all those rungs.
Exactly. But after hundreds of papers looking at every possible source of error, from dust blocking the light to the focus of the telescope, the consensus is that the local measurements are solid.
There's a really interesting theory about the supernovae themselves that shows just how hard it is to explain this away as a simple error. The metallurgy theory.
Oh, this is a great point. So a type Ia supernova's brightness comes from the decay of radioactive nickel-56 that's created in the explosion.
Okay.
And how much nickel-56 gets made depends on the star's metallicity.
Which in astronomy just means any element heavier than hydrogen and helium.
Right. So stars that form more recently, like the ones nearby, have higher metallicity because they're made from the ashes of previous generations of stars.
So local supernovae and distant supernovae should have different compositions.
And theory suggests that higher metallicity, more heavy elements, should actually lead to less nickel-56 being made in the explosion.
Which would make the supernova less bright.
Correct. It would make our local standard candles slightly dimmer than we assume they are.
So if we think a candle is standard, but it's actually dimmer, we'd wrongly calculate that it's farther away than it really is?
Exactly. And if we think it's farther away for a given velocity, that would lead us to calculate a slower expansion rate. It would push the h-naught value down, closer to 67.5.
That's a huge point. The most likely known physical error in the measurement would actually shrink the discrepancy, not create it.
The fact that the number stubbornly stays high at 73 suggests that if there is an error, it's something far more exotic than just standard stellar physics.
Okay, what about the other side? How reliable is the early universe data? The 67.5 is a prediction, not a measurement, right?
It is entirely model dependent. It's only true if the Lambda-CDM model is a perfect description of the last 13.8 billion years.
If there's a missing ingredient anywhere in that history, the prediction is wrong.
The whole thing falls apart. So people spend enormous amounts of time looking for systematic errors in the Planck data. You know, how they subtract the light from our own galaxy, small differences in the math they use.
But again, that internal consistency is their strongest defense.
It is. The fact that Planck, ACT, and the BAO data all converge on that lower value makes it seem very unlikely that all three independent methods are wrong in the exact same way.
So what about the last big idea for an error? The local void theory. Maybe we just live in a weird part of the universe.
This was a popular idea for a while. The thought was, what if we live in a giant cosmic bubble, an area with less matter than average? A void, yeah. If we're in a big empty patch, the gravitational pull from our surroundings would be weaker, so things would appear to be flying away from us faster than the cosmic average.
It would give us a falsely high reading on our local speedometer.
Exactly.
So what's the verdict on that?
It's been pretty definitively ruled out. To explain the tension we see, the void would have to be enormous and extremely empty. And cosmological simulations show that a void like that is just, well, it's incredibly unlikely to exist.
And our supernova data, which looks way beyond our local neighborhood, just doesn't show us sitting in a giant bubble like that.
Correct. So, to sum up, we've checked the local measurements. They seem solid. We've checked the early universe measurements. They're internally consistent. We've checked our local environment. We're not in a weird spot.
The conclusion seems almost inescapable.
It is. The difference between 67.5 and 73 is real. It's not an accident, and it demands new physics. Something is missing from the standard model.
This is where it gets really interesting. Let's get into the solutions. Section 4. Ideas from the early universe. Theories that try to change the cosmic blueprint before that baby photo was taken.
Okay. So, for any early universe fix to work, it has to do two things at once. First, it has to raise the final predicted value of h-naught up to 73.
And second,
It has to shrink something called the sound horizon.
the sound horizon. Let's focus on that. That's the cosmic ruler we talked about with the BAO, right?
Exactly. The sound horizon is the maximum distance those sound waves could have possibly traveled in the early universe before they got frozen in place. Its length is fixed by standard physics.
And the size of the spots on the CMB Davy photo corresponds directly to the length of that ruler, which, in the standard model, leads straight to the 67.5 prediction.
Right. So if we want that early universe calculation to suddenly spit out 73 instead, we have to find a way to make that fundamental ruler shorter than we thought it was.
Ah, because if the ruler you start with is shorter, the universe must have expanded much, much faster to get to the size we see today.
You've got it. We need a mechanism to speed up the expansion of the universe in that very early pre-CMB era.
And one of the leading ideas to do that is called early dark energy.
EDE, yes.
So just like regular dark energy, but on a timer.
In a sense, the idea is that a new temporary form of dark energy briefly appeared and dominated the universe for a short time, right around when matter and radiation were equal in density, and then, crucially, it had to disappear just before the CMB formed.
So it's like giving the universe a short, sharp turbo boost right before we took the picture.
A perfect way to describe it. That turbo boost would have accelerated the early expansion, which means the sound waves had less time to travel. That shrinks the sound horizon, the ruler gets shorter, and a shorter ruler allows the model to predict a higher h-naught today, potentially all the way up to 73.
Is there a physical mechanism for what this stuff could be?
One of the more popular models involves a hypothetical particle called an axion, an ultralight axion. The idea is that a field associated with this particle starts to roll down a potential energy hill. While it's rolling, it acts like a dense fluid, a form of dark energy.
It provides the turbo boost.
Right. And then when it reaches the bottom of the hill, the field settles down, the extra dark energy vanishes, and the universe goes back to its standard evolution.
But that timing has to be incredibly precise.
And that's the big problem with EDE models. It's called the cosmic coincidence problem. You have to fine-tune it to turn on and off in this very specific, narrow window of time. It can feel a bit engineered.
Okay, what's the other main way to shrink that cosmic ruler?
That would be adding extra relativistic particles, or what we call dark radiation.
Dark radiation.
The idea is that the early universe might have contained more types of fast-moving particles than we know about. We have photons and 3 types of neutrinos. This idea suggests there might have been more. The parameter we use for this is called N-effective, or NF. Yeah.
So, using our highway analogy again, this is like adding extra invisible traffic to the road in the early days.
Yes. And that extra traffic, that extra radiation, adds to the total energy density of the early universe. More energy means faster expansion. Faster expansion means less time for sound to travel.
And a shorter ruler. It's the same end result.
The exact same end result.
And what could this dark radiation be?
The main candidate is a hypothetical 4th type of neutrino, a sterile neutrino, that only interacts through gravity. Or it could be from something more exotic, like dark matter particles decaying into this unseen radiation.
So both early dark energy and dark radiation try to solve the problem by tweaking the universe before the CMB. But you mentioned there's a problem with these ideas now.
There is. The latest data, especially from the ACT telescope, is so precise that it puts really tight constraints on these models. The standard blueprint just fits that early data so perfectly. When you try to add in enough EDE or dark radiation to fix the Hubble tension, it often messes up other parts of the CMB picture that we've measured with incredible accuracy.
So if the problem isn't in the deep past, maybe it's more recent. Let's move on to solutions from the late universe.
Right. So now we're looking at models that change the expansion history after the CMB formed, sometime in the last few billion years.
So the goal here is different. We accept the cosmic ruler is the length we thought it was, but we're proposing that someone slammed on the gas pedal much more recently.
Exactly. The most straightforward way to do that is with late dark energy modifications. This means questioning what lambda, the dark energy part of the model, actually is. Maybe it's not a constant.
Maybe it's dynamic, it's changed over time.
Precisely. Maybe it's gotten stronger recently.
Okay.
There are models where the equation of state of dark energy is allowed to vary. In the standard model, this value, called W, is fixed at -1. But if you let it dip even lower than that,
It becomes even more repulsive.
exactly, it enters a phase some people call phantom crossing, and it drives a much faster late-time acceleration, pushing h0 up towards 73.
Is there a specific time this would have happened?
Some models propose a rapid transition in the density of dark energy sometime between, say, 10 billion and 5 billion years ago. A quick boost that would jack up the current expansion rate.
But what's the big challenge for these late-time fixes?
The problem is that h0 isn't the only thing we measure in the late universe. We also have the BAO standard ruler data and vast catalogs of supernovae.
And when you try to fix h0,
You often break the beautiful agreement the standard model has with those other data sets. It's like trying to fix one problem but creating 2 new ones. It's very hard to find a model that works for everything.
which has led people to even more exotic ideas, like interacting dark sectors.
This is where it gets really creative. The idea is that maybe dark matter and dark energy aren't just ignoring each other. Maybe they're secretly interacting.
A cosmic soap opera.
It is. What if there's a flow of energy between the two? If dark energy is constantly, say, draining a tiny bit of energy from dark matter, that would change the expansion history of the late universe in a very unique way.
That seemed like a promising way to change things recently without messing up the early universe.
It is, but again, these models are incredibly hard to constrain. Any interaction strong enough to fix the Hubble tension has to be weak enough that it doesn't also mess up the way we see galaxies and clusters of galaxies forming.
Which brings us to the most profound idea of all. Modified gravity. What if Einstein was wrong?
Well, not wrong, but maybe incomplete. This is the idea that general relativity, our rule book for gravity might need to be adjusted on the very largest cosmic scales.
How would you even do that?
Mathematicians and physicists are exploring theories with names like FER gravity or FT gravity, where they add new terms to Einstein's equations that could kick in over immense distances or at specific times in cosmic history.
And could that directly affect our measurement of H0?
Yes, and in a very clever way, there's a proposal for something called a screened fifth force.
A fifth force of nature.
Potentially. The idea is that this new force might exist, but it's screened or hidden in most of space. It only becomes active in very high-density environments.
Like inside the galaxies where we are measuring Cepheid stars.
Precisely. If there's a new force at play inside those galaxies, then our most basic assumption that a Cepheid in one galaxy behaves identically to a Cepheid in another could be wrong.
It would mean our standard candles aren't actually standard. The whole first rung of the distance ladder would be compromised.
Exactly. It would mean the 73 value is a real measurement, but the physics we're using to interpret it is wrong.
That's a mind-bending idea. And it's not like the Hubble tension is the only little crack in the standard model, is it?
Not at all. There are long-standing issues with dark matter, too, like the cuspy halo problem.
Right. The simulations say dark matter should be really dense and cuspy at the center of galaxies.
But our observations of how stars move show that the centers are much flatter. The theory and the observation don't match.
And there's the dwarf galaxy problem as well.
Yeah, the missing satellites problem. Our simulations predict there should be thousands of little dwarf galaxies orbiting big galaxies like our own. We only see a few dozen.
So where are they?
That's the question. All these little issues, plus the giant Hubble Tension issue, they all suggest that our standard model is incredibly good, but it's missing something fundamental.
We have come full circle. 2 hyper-precise measurements. 67.5 from the past, 73 from the present, and a gap that just refuses to go away.
It's the most solid piece of evidence we have for physics beyond the standard model.
So Lambda-CDM got us, 95% of the way there? But that last 5% is where the real mystery begins.
That's right. If H0 is the spinometer, it means either we totally misread the original roadmap because the ruler was shorter, maybe due to that early dark energy,
or someone has been secretly pushing the gas pedal harder than we thought over the last few billion years.
And the challenge now is to find a new piece for the model that fixes the speedometer without breaking the engine, the transmission, and everything else that works perfectly. And for that, we need more data.
Which is where the James Webb Space Telescope comes in.
Webb is absolutely crucial. It can do Hubble's job, but better. It can see those Cepheids and supernovae with much greater clarity at greater distances. It will either confirm that 73 value with even smaller error bars,
or it might find the systematic error that has eluded us for a decade.
If it confirms the 73 value, the pressure to abandon the standard blueprint is going to become immense. It will all but force us to accept that there's a fundamental new piece of physics waiting to be discovered.
This one numerical disagreement has basically turned the entire field of cosmology into the most exciting hunt for new physics in a generation.
It really has. It signals that the era of having a perfect model that explains everything might be over. We are genuinely on the cusp of a revolution in our understanding of reality.
And that's a thought worth holding on to.
Right.
We thought we had the blueprint figured out. But finding these cracks, these places where reality just refuses to match the model, that is exactly how science moves forward.
It's a humbling reminder, isn't it? That even with all our incredible technology, the universe still holds these deep secrets about its most fundamental components, all hidden away inside a single stubborn number.
Thanks for coming along in this deep dive with us. Remember to follow us on your favorite podcast platform, and see you on the next dive.